We want to take a look at solving logarithmic equations using properties of logarithms and the inverse property for logarithms. First, we need to recall when we have a logarithm, a product inside a logarithm, we could break it up into two separate logs. So the log of x times y is log of x plus log of y. Log of x divided by y is log of x minus log of y. Log of x to any power is that number, a, times the log of x. And we will also be using our inverse property. Any base a raised to the log base a of x is x. The a and the log base a work as the inverses. So we have an equation, log base 2 of x plus log base 2 of the quantity 2x plus 5 equal to log base 2 of 7. So first, what we want is to isolate the logarithms on one side of the equation. So we want the logs only on one side of the equation. And this isn't terrible because I have this log base 2 of 7. I could subtract it to the left side. So we will have log base 2 of x plus log base 2 of 2x plus 5 minus log base 2 of 7 equal to 0. All of our logarithms are isolated on one side of the equation. Now we're going to use our properties of logarithms to combine our logarithms. Notice we have addition and we have subtraction. So we want to combine our logarithms into one single expression. Log base 2 of x plus log base 2 of the quantity 2x plus 5, I can write in terms of a single logarithm. Because of the addition here, we will have x and the 2x plus 5 being multiplied together. Because of the subtraction, remember subtraction is for our division, we would have 7 as a divisor. So our three separate logarithms, log base 2 of x plus log base 2 of 2x plus 5 minus log base 2 of 7, all combine into one logarithm. Anything positive, those things being added in the numerator, that one term being subtracted in the denominator, that one single logarithm equals 0. But now that we have a single logarithm, we can exponentiate these. The base for our logarithm is 2. So we're going to use base 2 to exponentiate. I will have 2 raised to the log base 2 of big angry bunch of stuff, x times 2x plus 5 over 7 equal to our base 2 raised to the 0. So the right side of the equation becomes an exponent, the left side of the equation becomes an exponent for the number 2. And we use the number 2 because we had a base of 2 in our logarithm. This is where our inverse property comes in. Because we have 2 and log base 2, these guys are inverses of each other. They will cancel out, leaving me the x times the 2x plus 5 divided by 7. On the right hand side of the equation, 2 to the 0 power is equal to 1. What we have now is a new equation that we can solve. Now we can take a look at solving the equation x times 2x plus 5 over 7 equal to 1. And I'm just going to go ahead and multiply 7 to both sides of the equation. I will have the x times 2x plus 5 now equal to 7. Distributing, we're going to have 2x squared plus 5x equal to 7. This is now a quadratic equation. We solve those by setting them equal to 0 first. So subtracting 7 from both sides, we have 2x squared plus 5x minus 7 equal to 0. This happens to be factorable. 2x times x for the 2x squared, 7 and 1 for the 7, and I need a positive term, so I'll make the larger one positive. We're checking, and yes, we have a good factorization. Now we can set each factor equal to 0 because the only way for two things to multiply out to 0 is if one of them is 0. So either 2x plus 7 is equal to 0 or x minus 1 is equal to 0. Solving the left equation, subtracting 7 yields 2x is equal to a negative 7, so x would be negative 7 halves. On the right equation, I could add 1 to both sides, and I get that x is equal to 1. Keep in mind, we found two solutions, but I don't know that I have two solutions to this equation. In fact, we need to check. And immediately, I know I cannot use that negative 7 over 2. Why the heck not? Because we're talking about logarithms. Log base 2 of negative 7 halves is not even defined. If you remember the original equation, it had the form log base 2 of x plus log base 2 of the quantity 2x plus 5 equal to log base 2 of 7. We could not use the negative 7 halves. The first logarithm would have been undefined. So now we can check if x equals 1 is a solution, and I think this one will be all right. Log base 2 of 1 plus log base 2 of 2 times 1 plus 5 equal to log base 2 of 7. Log base 2 of 1 is 0, and 2 times 1 is 2 plus 5 is 7. We have a true statement because log base 2 of 7 is exactly equal to log base 2 of 7. So this checks x equals 1 is a solution. X equals negative 7 halves would not be a valid solution for our logarithmic equation. We can stop there.